So for those of you who don't know me, which is probably most of you, I'm actually Dorothy Duffy, and I'm Emeritus Professor of Physics at UCL. So I did actually retire a couple of years ago, but I was still involved in some projects at UCL. So just want to confirm, is my audio clear? Can everybody hear what I'm saying?
Yeah, I can hear you just fine.
Okay, that's good. So interrupt me at any time with questions, and I will stop every now and again and ask if anybody has any questions. So the topic of this lecture is classical interatomic potentials. And the overall aim is to give an overview of all the commonly used interatomic potentials for a range of classes of materials. So the best interatomic potentials are actually those which have based on physics. So what we're trying to do is encapsulate the quantum interactions in classical potentials. And we use functional forms that actually reproduce the physics of the interactions. So that's going to come through a lot in the potentials I'm going to show you today. Yeah, there we go. So this is an overview of the plan of the lecture. I'll start off with the advantages and limitations of classical potentials and discuss why we want to use them at all. And as I said before, we're going to focus on physics-based potentials. So we want to relate the functional form of the potentials to actually the type of bonding we have. Then I'll discuss the simplest of all potentials, which are two-body potentials. And I'll finish this part of the lecture with a case study, which are basically of phase transitions in ferroelectric crystals. And I'm choosing this because it demonstrates how these actually relatively simple potentials can reproduce quite complex behavior, which we see in these very complicated crystals, ferroelectric crystals. Then I'll move on to more complicated types of potentials. These are multi-body potentials, which are good for organic molecules and biomolecules, many-body potentials for metals, and then many-body potentials for covalent solids, which have a different functional form. So all these types of potentials have different functional forms, and the aim is that they encapsulate the type of bonding, the quantum mechanics of the bonding between all the atoms in the crystal. I'll finish off with the third part, which are the most complicated potentials I think have been developed to date and are the most ambitious anyway. And these are the FF potentials. And these want to be able to describe complex chemistry and actually bond-breaking information. I'll finish off with giving you some ideas about how to choose potentials and summarize the lectures. So why bother with interatomic potentials? We all know nowadays that DFT is very powerful, quite accurate, and we can go to at least quite large unit cells. It's very efficient. But even so, the classical potentials are orders of magnitude more efficient. Therefore, you can extend the length scale up to micrometers in some cases, and the time scale up to at least nanoseconds, many nanoseconds, tens, hundreds of nanoseconds. So you can go to much larger simulations and much longer time scale simulations. Of course, there are limitations, and we said they are models. And as George E. Box, a famous statistician, once said, all models are wrong, but some are useful. I think this is actually becoming quite apparent during this epidemic as people keep criticizing the models and not actually getting the right answers. So they're all wrong, but we have to know the limitations. They may not be reliable outside the range that you've used to fit them, because all of these potentials are fit to either experimental data or density functional theory calculations, and you fit certain characteristics. And if you try to model different characteristics, they may or may not work. Transferability is a problem. For any particular material, you have to actually consider the potentials for that material. You can't take the oxygen atom from water and use the potentials for that, the oxygen-oxygen interaction for that, and transfer it to, say, magnesium oxide. That doesn't work. And clearly, you don't get any information about the electronic structure or the electronic properties of material. So there are limitations, but there are advantages. So the advantages, basically very large length scales, and this is very important for a number of systems, particularly disordered materials, such as alloyed glasses. The larger the unit cell, the more, because the periodic unit cell, the more disordered your material is. So you can capture the disorder, which is fundamental to your material. Also things like surfaces, particularly things like complex surfaces that want to restructure, or adsorbents, molecules on surfaces. If you want to do dilute absorbents, then you actually have very large unit cells. Same is true for grain boundaries, domain walls, dislocations. These are all very large scale defects, so you need large unit cells. And clearly things like polymers and nanoparticles also need large unit cells. So a lot of these systems are things that can't be treated in a satisfactory way with quantum simulations currently. Also in terms of time scale, if you want to model non-equilibrium processes, diffusion, thermal conductivity, you do need long time scales. Things like fracture and protein folding, obviously very long time scales, cannot really be tackled with density functional theory. And if you want to calculate free energy surfaces with systems such as metadynamics, in order to get convergence of these, you need very long timescale simulations. So classical methods are usually the only way we can go forward with this. So when we're undergraduate, we learn that there are 4 types of bonding: ionic, covalent, metallic, and secondary bonding, such as van der Waals interaction. So material science perspective, that actually translates into 3 types of materials. Ceramics are bonded with ionic and covalent bonding. And when we do ceramics from a material science perspective, it's a bit broader than what we think of in everyday life. We think of ceramics and things made of sinks or coffee mugs. It's anything really that has a strong ionic or covalent character to the bonding. And these basically means these are very large bond energies, very high, which lead to high melting temperatures, very stiff materials, and small thermal expansion. Of course, metallic bonding gives particularly different properties, and the most important properties of metals in terms of the mechanical properties is that they're ductile. So they'll bend rather than break if you drop them. Polymers have got a combination of very strong covalent bonds within the molecules and much weaker secondary bonding between the molecules. So they are generally weaker. They can be ductile, they can be brittle depending on the amount of covalent bonds, and they generally have low melting temperatures. So the bonding really determines all the properties of material. So this is what we want to capture in our interatomic potential models. So we're going to start off with the simplest potential, and these are 2-body potentials. And the definition of these basically is that the cohesive energy can be written as the sum of the pairs of the energy, of all the pairs of bonds in the material. So this basically means that the interaction energy between any 2 atoms of material doesn't depend on the positions of all the other atoms around it. And that means we can divide it into this simple functional form. I'm going to cover 3 of these well-known types of potential. The Leonard Jones potential, I'm sure you're all familiar with it. And that's basically used for inert gases, but widely used now for intermolecular interactions between polymers and biomolecules. We're going to talk a little bit about the Morse potential, and that's particularly relevant to the covalent bonds in small molecules, not in the large polymer molecules. And we're going to finish off with the Buckingham potential and the Coulomb interaction. And these are actually used for ionic crystals. So briefly, I'm going to talk about the Leonard Jones potentials. As I say, I'm sure you've covered it before, but just to talk a little bit about where they come from. So it's a sum of an attractive term, which falls off as R to the -6. And this is the attractive interaction is due to the dipole interaction between the atoms and materials. They can either be induced dipoles, which is be fluctuations of one charge cloud will actually induce fluctuations in a nearby cloud, or they can be permanent dipoles. So this is basically this R⁻⁶ is a physics-based fall off with attractive interaction of distance. We obviously, when it gets close together, we have to add another repulsive term, because as you get the atoms get close together, you get overlap of the atomic orbitals, and this induces a Pauli repulsion. So we want to find a way to represent this. So in the van der Waals interaction, it's actually represented as R⁻12, or R⁻12. So as you get close together, you get a very strong repulsive term. So the choice of the R⁻12 is historic. Basically, it was written in the day when it was computational power was actually very limited. Therefore, it's very efficient to actually have it as the square of the R⁻⁶ term. So there's no physical justification of the R⁻12 other than the fact it actually goes to infinity quite quickly, and it represents a strong repulsion. So the Leonard Jones potential has got two parameters. One, epsilon, is related to the bond strength, as you can see from the picture at the bottom. You see the depth of the well is basically epsilon. So strong bonds with deep wells. And then there's the size of the atom. So it's basically the sigma term. So bigger, larger atoms will be further apart and then have a larger sigma. So as we say, that these are actually very successful, very easy, very efficient, but limited in their use to basically either inert gases or large organic molecules. And basically the interaction between the atoms and the molecules, interaction between different molecules and these large ones is what they're used for. So that's all I'm going to say about the Leonard Jones potential. Then I'm going to move on to the Morse potential. And these are really appropriate for the covalent interactions that can take place between the atoms and small molecules, typically things like nitrogen, carbon dioxide. So it's basically the main feature of this is it's anharmonic. When we model the bonds, and we'll see later on, between the atoms in a polymer, a large organic molecule, we'll tend to use the harmonic potential. This isn't really appropriate for these small molecules because they move outside their vibrations, they move outside their harmonic region. So if you want to capture this anharmicity, we use the Morse potential. And it's this functional form. It has got, you can see the anharmicity from the plot, the Morse potential plot. So the three parameters is actually all got physical meaning. One is the dissociation. So this is the energy required to move the atoms from the bonded state to infinity. Obviously the RE is the equilibrium bond distance, and the alpha is a measure of the anharmicity. So these actually can all be derived from experimental parameters. So we can get very accurate parameters for these Morse potential for these small molecules. So finally, for this type of two-body potentials, perhaps the most important and most widely used ones are the potentials used for ionic crystal. And these are a combination of the Buckingham potential and the Coulomb interaction. So the main interaction between the atoms or ions in ionic crystal is the Coulomb interaction. So we always know that the Coulomb interaction can be written in this equation, so well known. But of course, if these get very close together, you need other terms. We also need to encapsulate the dipole-dipole interaction, and we do this in the same way as we would do for the Leonard Jones potential, for R⁻⁶. But instead of the R⁻12 function that we use for the Leonard Jones potential, here for the Buckingham potential, we use an exponential repulsion. This captures and maybe better encapsulating the true quantum mechanical repulsion, Pauli repulsion at short distances. But I think more importantly than that is we actually have three free parameters here, and that gives us better flexibility in fitting. So that may be the main reason that we use these three parameters. There is one thing you need to be aware of the Buckingham potential, and this is a potential instability. And as you see, we have a plot down here. Basically, this is what the Buckingham potential looks like. So instead of going off to plus infinity, like the Leonard Jones potential, it turns around and goes off to minus infinity. And you can see this quite clearly. If you look at what happens at r equals 0, this term becomes A. So it doesn't go off to infinity at r equals to 0, like the r to the minus 12 term. It doesn't usually matter, because usually we do our simulations close to equilibrium, to close to the bottom of the well. But sometimes if you start an academic simulation and it's far from equilibrium, the forces can be large enough to actually cross this barrier, and the simulation will fail quite quickly, and you might wonder why, but that's obviously something you need to be aware of. And in that case, you need to go back and get rid of all the large forces before you restart your simulation. So that's basically how you model ionic crystals. But of course, the ions in ionic crystals are actually intrinsically polarizable. And this is sometimes important. So this basically means you've got the ions and you've got the core. And if you apply electric field, the electrons go in one direction and the core goes in a different direction. So this has been modeled for several decades, more than that, with a core shell model. So what we do is we have a positive core and we have a negative shell. And these are joined together with a harmonic spring. So that means if you apply electric field to the ions, you get a separation, a core shell separation. And this captures the polarization, which is actually very important in some of the applications of these materials. So if you wanted to model diffusion or perhaps phonons, it's often quite important to actually capture this polarization, in which case you want to use a core shell model, or shell model. So basically, this is the parameters needed for the harmonic spring. So what we're saying here is we can model ionic crystals quite successfully by using a combination of Coulomb interaction, Buckingham potential, and the shell model. So I just want to finish off this part of the lecture by talking about one example. And this is a model, a ferroelectric material, a very important ferroelectric material from a technological point of view, which is called PZT. It's lead, zirconate, titanium oxide. And you can see that basically it's an alloy, a random alloy of two ferroelectrics, which is lead, zirconate oxide, and lead titanate. So X here, for a technological point of view, tends to be round about 0.5. So it's round about a 50-50 proportion of zirconium and titanium. So PZT is a very important ferroelectric because it's an exceptional piezoelectric response. So if you put a very small strain in the material, you induce a very large dipole moment. So it's very sensitive. Conversely, if you put an electric field, you induce a very large, horribly large strain. So they're used widely for sensors or transducers. Transducers would change strain energy into electrical signal, or even capacitors. And because they're such an important technological material, it's quite important to be able to model them. But the challenge for these is trying to do this with DFT when it's actually a random solid solution is very challenging. You need very large unit cells. So what you actually want is a very good interatomic potential that represent these materials so they can do simulations, classical simulations with it. So these materials have got perovskite crystal structure. So above a critical temperature, the ferroelectric temperature, they've got a cubic structure. And in this case, they have got the lead ions in the center, in the corners of the cubic cell, the oxygen ions in the center of the cubic cell, and the titanium or zirconium ions in the center. So the oxygen in the face center, the zirconium or titanium in the body center. So above TC, everything's symmetric, and you don't actually get any polarization. But below PC, you get a distortion. This can be a rhombohedral distortion, or here shown a tetrahedral distortion. So basically, the unit cell distorts in one direction, and that means also the central ion moves off center. So each unit cell has got a polarization, and that means that your crystal itself has got a polarization below TC. Above TC, you've got zero dipole moment or zero polarization. Below TC, you've got a dipole moment. So how to actually model this? Basically, we want interatomic potential that will reproduce this very complicated phase diagram. And it's complicated because the crystal structure is different if it's titanium rich on this side of the phase diagram, or if it's lead rich, or zirconium rich. So when it's zirconium rich, you actually get a rhombohedral crystal structure, and when it's titanium rich, you actually get a tetragonal crystal structure. And of course, above TC, and this is temperature plotted against the composition. So from here, you're increasing the amount of zirconium ions till you get to the PTO, which is lead titanate. So above the critical temperature, it's cubic, so there's no polarization. You reduce the temperature and you get a transformation either to tetragonal or to rhombohedral. But the interesting part of this phase diagram is a bit in the middle. So this is when you actually get a competition between the rhombohedral tetragonal crystal structures. You get what's called the morphotropic phase boundary. And this means that the crystal is a bit confused as to which way to go. So it actually becomes monoclinic. So what we want to do would be develop a potential that will capture this behavior in order to have a good potential if we can do simulations in. So it's an ionic crystal, so we can use the bucking potential, Coulomb potential, and the shell model. We've found that actually for the shell model here, if you had to add a quartic term, because these ions are so polarizable, the displacements got too large if you just had a quadratic term. So you had to modify the shell model slightly, and this has been done by other people for lead titanate. So you modify the shell model, but other than that, it's just a standard Coulomb potential and bucking potential. So I'm just going to say a few words about fitting the potential, just to demonstrate that fitting potentials is not something to be taken on lightly. You have to go through a number of different processes, and you have to choose what you're fitting it to very carefully and go through a different stage of fitting. So here we start with a well-known, well-established PTO potential that was parameterized. And then we optimize the Z, leave the lead, oxygen, and oxygen parameters unchanged, but fit the Z, oxygen, and the zirconium oxygen parameters and fit them to various DFT calculations. Once you get a satisfactory answer for this, you have to worry about fitting to all the different crystal structures. So you modify it a little bit so it fits the tetragonal, the rhombohedral, and cubic crystal structures of all the different materials. And then the ordered phase of PZT, which is actually tetragonal. And then when you fit all those, you do some more tweaking in order to get the Bowen effective charges relevant to the polarization and the elastic constants and all the other properties that you want to fit to BFT. So it's a very long, drawn-out process. And this is also something that actually shows you that the fitting potentials is not something to be taken on lightly. You have to decide which properties are important to you and what the errors are, what errors are acceptable. So basically what I'm showing you this for is you have to go around the loop many times just to fit one of these properties. And then you want to add different properties as you go along. So in the end of the day, we get potentials that work. So I'm not expecting you to take anything from these numbers, only two things, which is basically we get all our interaction potentials for the bucking potential. And basically the important thing here is we want to look at the charges. The charges you get for the core and the shell are very large, but you add them together and you realize that actually the total charge of the lead is relatively small, and smaller than you would go for the two that you would get if you used formal charges. The same for oxygen and zirconium, titanium. And these are relatively small K2 for quite weak springs. So the lead and the oxygen are very polarizable. So these actually capture the polarizability of the lead and oxygens very well, and many of the properties of these materials. So does it work? Well, in order to find out whether it works or not, we can do some very large-scale simulations, NPT simulations. So we let the molecular dynamics simulations, we let the shape of the unit cell change. So quite large unit cell, we let the shape change. And then we actually work out what the lattice parameters are and how they change with temperature. So these just show that we can capture the rhombohedral structure, and the tetragonal structure, you can see that the A and the B parameters are the same, but they're different from C. And all the angles here are 90 degrees. So this is tetragonal. This is for the PTO, which we know should be tetragonal. And then you increase the temperature. The lattice parameters get closer and closer to the critical temperature, around about 550. They become the same. And they're now cubic. So this one here is actually the 50-50 PZT. And you can see it's quite complicated, but the main point here is that all the sides are different. So it is monoclinic. And then the other thing we can calculate from these is polarization. So for my molecular dynamics simulations of these materials, we can calculate the polarization. And again, we expect this to decrease to zero because we're above the critical temperature of the zero polarization. So we plot that. And the blue line is actually PZO, and that is actually antiferroelectric. So you wouldn't expect any polarization. So again, they seem to capture the main points. They capture the structural transitions, and they capture the ferroelectric transition. So they're pretty successful. So we can do many other things with these quite simple potentials. So one of the important things about these materials is you make very thin films out of it. You get very interesting domain effects. So it will break down into different domain structures. And as you apply different strains, you get different domain structures. And under certain, if you change the temperature or the strain, the domains do different things. So these materials, this PTO, is actually one of the materials that's actually possibility to make memory materials from, because you can make these very interesting domains. And these potentials actually capture the main effects of these domain structures. So these arrows here that you can see in these pictures represent the direction of the polarization, and the color direction, the strength. So when you see the arrows going from up to down, this is different just like ferroelectric domains in your material. So that's basically it for the two-body potentials. But just to say that you don't always have the potentials you need for the material you need. You might have, you know what AA will interact with, and you know what BB. So can you actually guess what the interaction between A and B is? And to do this, you might consider mixing rules. So these are very widely used for van der Waals interactions, particularly when you're talking about organic molecules. There are many different types of atoms in organic molecules, and you can't possibly hope to for all the different materials to have different interactions. So what you've done here, that if you know the carbon-carbon and the nitrogen-nitrogen interactions, you can actually derive the carbon-nitrogen interactions using these mixing rules. So what you do is you take the arithmetic mean of the length parameter, the sigma parameter, and the geometric mean of the epsilon parameter, and you use these for mixing rules. So these are very widely used for organic molecules. But in terms of the Buckingham potential, there isn't any simple, reliable. There is a way, there is an equivalent sort of mixing rule if you rewrite it in a different form. However, I wouldn't ever, the only reason for using these would be as a starting point for deriving better potentials. I don't think anybody has ever claimed that these mixing rules work for organic materials. So only use them if you're going to rederive the potentials using other methods. So to summarize, I think hopefully we've shown here that these carefully parameterized potentials can model complex phenomena. They're actually really efficient, and it's quite standard to use multi-million atom simulations for nanosecond timescales because they're very efficient. So we can do complex materials and do large-scale features using these and very large timescale processes. So that's actually the first part where we're talking about two-body potentials. Does anybody have any questions at this point? Shall we move on? Yep. Okay. So those are the simplest of all types of potentials I have just discussed. Now I want to move on to multi-body and many-body potentials. So I've said that for two-body potentials, you can write the cohesive energy as the sum of the interaction between pairs of atoms in the material. For some materials, this really just doesn't work. And these include things like large organic molecules, where we use multi-body potentials, and metals and covalent solids. Such potentials will not describe the physics of these materials. So we do different types. So when I talk of multi-body potentials, I mean basically potentials that can be written as 2, 3, and 4-body terms. And the common ones of these is basically large covalently bonded molecules, which are important in polymers, proteins, lipids, amino acids. So basically all the bio modeling use these type of potentials. There are some of 2, 3, and 4-body terms. So 2-body terms basically means bond stretching, so interaction between two atoms, strangely enough. 3-body potentials, basically we need 3 atoms, the positions of 3 atoms to define the angle. And the dihedral angle needs the position of 4 atoms. Basically, the angle between rotating bond Ij about and Kl about the bond Jk. So the energy of these interactions will depend if you rotated that. So this is basically what we talk about for the dihedral angles. In terms of all these 3-body, we also need to include intermolecular interactions. So these 3 terms will describe the intramolecular interactions, the energy of the molecule itself, but then all the molecules, not maybe in a protein, well, even in a protein, the molecules will interact with other molecules, and we need to include Leonard Jones potentials, which are with mixing rules, as I said before, to describe this. And all of these atoms, or a lot of these atoms and these things, have got partial charges, so they also interact with Coulomb interaction. So if you're going to use these type of biomolecules, organic molecules, I'd highly recommend you read this very good review published in 2018, which is very comprehensive and give a lot more detail than I'm giving here. Multi-body potential, because they're so important for biomolecules, there have been a lot of standard force fields which are under continuous development and become better all the time. I've mentioned some here: Gromos, Amber, Charm, and OPLS. So there's usually a function both for small molecules and for these large molecules, different potential parameter sets. Here I've said UA and AA. UA means united atom. So some of these potentials will actually just never include hydrogen explicitly. They always add their hydrogen either to a carbon or to a nitrogen. So that means united atom. There's a big advantage in this in terms of efficiency. So not only obviously you have less atoms if you don't include the hydrogen explicitly, but also hydrogen is very light. And if you're ever modeling hydrogen in molecular dynamics, you have to use shorter time steps because of the very high vibrational frequency. So you can see Gromot's united atoms. Some of them have, but you can use all atom if you prefer, if you think the hydrogen atoms are important. So it's a choice you have to make. And this is basically the same as I wrote before, where you have the general form of these types of potentials are basically you can sum over the bonds. These are the two-body potentials, and these are generally chosen to be harmonic, unlike the anharmonic one, the Morse potentials I showed you before. They're generally chosen to be harmonic. The vibrations are never usually large enough to worry about anharmonicity for these. And the harmonic angles, dihedral angles, when you rotate it, there could be a number of different minima in the entity, so it's got a slightly more complex form. We also often need to consider improper dihedral angles. Improper dihedral angles really are a way of actually, it's an angle between, if you look at this picture down here, the plane subtended by I, J, and K, and the K, J, and L. It gives you an angle. So if you give an energy penalty when this angle deviates from zero, so they, or whichever the minimum is, often zero, then that will keep these three atoms in plane. So it stops these atoms binding out of plane, which is sometimes important. And then we want to include, as I said before, the Coulomb interactions and the Leonard Jones interactions. So parameter sets for basically for many, many different types of atoms, but you also need to say there's not just one type of carbon atom. There's carbon atoms that are doubly bonded, carbon atoms that are bonded to different atoms. So wherever the environment is, you have a lot of different types of these atoms, particularly for carbon, but also for nitrogen and oxygen as well. So there's a lot of parameters in these models, but fortunately you don't have to worry about them too much because they're all in these standard force field parameter sets, which are also very good, very reliable, and they all come, but these very efficient codes. Again, you've got a choice of codes, all very efficient, highly parallelized, and widely available, widely freely available. So it's quite generally reasonably easy to do this well, do these sorts of simulations.
Excuse me, I have a question related to those force fields. Do you know which were the target properties they were fitted to?
Many, usually DFT, structural information, barriers. When you're actually like rotating a dihedral angle around it, you can calculate these things with DFT. So we'll say how energy penalty for rotating things, energy penalties using DFT for bond bending, that type of thing. So I think largely they're fitted to quantum calculations. Also probably some, in some cases, some structural experimental properties, but just generally. But yeah, I think it really depends on the application because they are large biomolecules. I think it's generally when they take smaller section like an amino acid and do lots of different calculations for the structural properties, different configurations of these amino acids, and then fit them to that, bits of proteins, that type of thing.
Okay, thank you.
Okay, thanks. So I just wanted to highlight, I haven't looked at this in great detail, but clearly since it's very topical. So what about the SARS-CoV-2 virus? What is being done? It seems that from a quick survey, quite a lot has been, as you might expect, quite a lot of people are trying to model, and particularly the spike protein is shown here. So I've just highlighted one paper. A lot of these ones are considering binding of the spike protein to different therapeutic drugs because they want to see how well the drugs will act. So a lot of the models are doing that. This one that I picked up here, I thought was quite interesting. It's looking something different. So this is a model of the spike protein. There's a lot of biological stuff in here that I can't complain to understand, but I think these different colors represent different domains of this particular protein. But the interesting bit is actually the blue bit at the top, because that's a receptor binding domain. So that's the important bit in some respect, because that's the bit that actually sticks to the ACE2 receptor in whatever part of the body it decides to attack. quite often the lungs. So this bit here has to stick to the ACE2 protector. So people have actually been looking at what happens, these particular simulations, looking at this particular area. They run the whole spike protein surrounded by glycans and surrounded by water. They're not really shown in this. And they run it for 1.7 million simulations in what they call a realistic environment. And they run it for 3 microseconds. And what they're looking at, whether this domain is open or closed. Apparently, if I understand it correctly, it has to be open before it will attach to the ACE2. So when they watch whether it opens easily or not, and what happens if you actually do some modifications, and whether it's disrupted by various mutations. And it found that this particular mutation would actually reduce the binding 40% reduction to the cell, this H2 cell. So this is the beginning of infection. Nothing's going to happen unless this part of the protein actually can bind to these receptors in your lungs. As I say, this is not my area of expertise, but I was just interested to see the type of simulations that people were doing. There's a lot of binding to various drugs. Another one I actually found recently just popped up in the New York Times, which I sometimes look at, is I think a very impressive simulation in terms of time and length scale, if not really results as yet. Maybe they will come. So they've modeled all of the virus, and not only that, they've put it in a droplet, an aerosol droplet. And so the concern is here, how long does the virus survive in an aerosol droplet? Obviously very topical, but whether this simulation will ever give the answer, I'm not sure. So the aerosol actually considered of not just water, but of also mucins, surfactants, other things you might expect, I suppose, if you coughed and you an aerosol. So they ran the whole 1.3 billion atoms for 10 nanoseconds, and they're still running for longer. And I think they're doing different variants, particularly Omicron variant, to see if they behave differently. So hopefully that will, after all that computational power, will give them some answers to what's going on. So any questions about that? I don't pretend to be an expert in biomaterials modeling, but that's I just find it interesting they can do such history. Obviously, I think that for this one they used the Oak Ridge supercomputer, which is, they claim, the second most powerful in the world. So they've used a lot of computational time. Impressive and ambitious. Any questions, which I may or may not be able to answer?
In that specific work, do you know which force field did they use?
I don't know. I mean, actually, I didn't actually find anything published, and it probably isn't as published yet. It just seems to be, this was just a New York Times article.
Okay.
It's bound to be one of the standard ones that are all pretty much of a muchness as far as I see, in terms of efficiency and accuracy, but I don't know which one. It'll be one of the ones I mentioned, I'm fairly sure, because they're so widely used and very efficient. And I don't know which program they used either, but I would think it's one of the same.
Okay, thank you.
Okay. So that's multibody potentials. So I want to make a distinction between multibody potentials and many-body potentials. So the difference between the interaction between the atoms and metals and the interaction between these biomolecules is obviously there's no covalent bonding. So in a metal, the interaction between any two atoms depends on the positions of all other atoms. And that is because, as you will learn from your undergraduates, when you think of metallic bonding, you think of the bonding being through a sea of electrons. So you don't get bonding between two atoms. You basically get a cohesion is related because you've got the sea of electrons and you've got all these positively charged nuclei, which are all held together with all this sea of electrons. So this is a quantum mechanics that we're trying to reproduce with our classical potentials. So the atom is embedded in the potentials. Our atom is embedded in the electronic density of all the valence electrons in materials. And this is it. Was first really put into interatomic potentials by Don Basque in the early 80s, but I think it was quite an impressive leap, because before that people were trying to model metals using two-body potentials, which was not working at all, and they couldn't reproduce it. So this is Don Basque's two classic papers, and this equation he shows you the functional form of these type of potentials. There's two parts. One is quite familiar. It's a two-body potential. It can have a repulsive part and an attractive part. But the interesting bit is actually what's called the embedding energy. So embedding energy function is a function of something called rho, and rho is actually taken from the position of all neighboring atoms. So basically that means if you've got an interaction between atoms I and J, then if you move J, if you use K, a neighboring atom, then you change the interaction energy between I and K. So basically you can't just write it as two-body potentials, because what's happening between I and J depends on all the neighboring atoms. So now you've got three functions. You've got the capital F rho, which is called your embedding energy function. You've got your density function, which depends on all the atoms around your atom I, and you've got your two-body potential before. So these three functions can either be tabulated or they can actually have functional forms. So there are many different ways of writing this, but they all are fit to generally, usually DFT calculations. So you have to fit three functions. So even though it's called the electron density, the relationship between electron density is not very, very robust. It's trying to represent what would be clearly if you have more atoms, you might expect more electrons, but probably that's as far as you go. But the type of the function of potential is trying to represent this effect. And this is basically the same thing, but shown a bit more schematically. So you've got all your green atoms in the material, and you've got a two-body term, which only lies on the distance between our I and J. And then you've got your I atom embedded in electron gas, and that comes in position from all the neighboring atoms. So that's why it's a many-body potential. So you can't just stop at 4, there may be 12 atoms around that are included in this, or even more. Okay. So the different types of many-body potentials. One of the most famous is Finis-Sinclair. So they went a step further, and others actually connected to the physics. They actually made the embedding function f of rho as a square root of proportional to the square root of the density. And that's important because there's a very strong link to that in simple tight binding theory, because that's what it would be in tight binding theory of cohesion. And this actually reproduces the parabolic variation of the cohesive energy across the series. That's actually, so if you actually build the D band, the density of states, you get this particular variation of cohesive energy. And it means that the local bond energy will vary as a square root of the number of neighbors. So the more neighbors you have, the bond energy decreases. So if you think of the energy of interaction between two atoms and you bring another atom close by, you will actually reduce the bond energy between them. And that will vary as a number of neighbors. So the more neighbors you have, the weaker the bonds. And that's a very important part, and that's actually true for metals. There are some limitations because obviously some particular BCC metals have got some, this gives you no directionality at all. This only depends on the number of neighbors. So in order to actually put directionality, which actually some body-centered cubic metals have, you have to modify this. And so there's now basically these types of potentials for all types of metals, and they're really successful. So the properties, As I said, that before the 80s, people tried to model metals using various types of power potentials, and none of them worked, especially for the elastic constants. Power potentials give you certain relationships between the different elastic constants of the material, and metals don't have this potential, this relationship. So they couldn't reproduce the elastic properties of materials. And also plastic flow, because these power potentials have a certain directionality of them. Plastic flow is very much enhanced if you use these embedded atom type potentials. Vacancy energies with power potentials are significantly overestimated because it doesn't include the fact that they, as you add more neighbors or take away more neighbors, you actually reduce the strength of the bonds, and the surface properties are wrong. So basically they relax outwards for power potentials, but because you've reduced the number of neighbors, the bonds in the surface get stronger. So in terms of metals, the atoms relax inwards when you make a surface. And the phonon dispersion were much more reliable for these potentials. So before I go on to this one, I think we'll take I'll take any questions, and then we'll take a 10-minute break before they do the rest. So we can all refresh. So any questions? Okay, so we'll start again at 2:05. Okay, I'll take a bit of a break. Okay. Okay, restart now after the break. So I've one more type of potentials that fall under the category as many-body potentials. And that's the potentials that are relevant for covalent solids. So what I mean is completely covalently bonded solids, the classic ones being silicon and carbon. So they've got some similarities with metals in that you have to modify the strength of the bond, the interaction between atoms, depending on the number of neighbors there are around. But they're very different in that they're actually covalently bonded. So we need a different functional form for these type of interactions. These come under a general category, we would say environment dependent interatomic potentials that have a general functional form shown here. So as before, we've got a two-body repulsive term, and we've got a two-body attractive term. With the two-body attractive term, the important thing about here is that it's modified by a bond order term. So this is basically where all the physics is encapsulated in here. And I'll talk about that in more detail in a moment. But the other thing is, as it is all multiplied by a cutoff function. So the cutoff function is important because it actually you only want the neighbors to interact if they're covalently bonded. So if something too far away shouldn't be interacting. So only you want to use the cutoff function to choose the atoms in your material that are bonded together. So you don't actually, like in a polymer, you'd actually put this in explicitly in your simulations. Here you use this cutoff function to look at where the distance is and how they. So this cutoff function will go smoothly from 1 when it's quite close together, and Rij is close together, to 0 when it gets beyond where you expect the two atoms to be covalently bonded. So this plot down here actually will show why we need such things. So basically, this is carbon-carbon interactions calculated, I think, using DFT. So if for a triple bond, you can see that the blue in here is very strong, very deep, very close together. As you go to double bonds, it's a little bit shallower, so this bond's weaker. And similarly, as you increase the number of neighbors in your atoms, if you right up to FCC, where you surround basically one carbon with 11 more carbons, 12 more carbons, then it's very weak. So this is a type of behavior that you actually want to capture in your covalently bonded material. And it's done with these environmentally dependent potentials. Probably the earliest, and believe it or not, the simplest one of these type of potential is a tensor potential. And it's probably the fastest one, and it's quite successful for diamond, structured carbon, and silicon. So here we have all the relevant equations, and it's not quite as horrendous as it might look at first sight. But I think what you can tell straight away is that there are a lot of free parameters in this model. So they basically, before you even look at the functional forms, you've got the A, B, lambdas, alpha, the thetas, minimum theta here. So a lot of parameters you actually have to use to fit these. So it's very challenging, and not too many people would have tackled this. So looking at our interaction between atoms I and J, this is our cutoff function, and this chooses which atoms will actually interact with each other, or which ones are actually too far away to be covalently bonded. And this is defined out here quite simply. So it goes 1, and then it goes continuously. It starts from R1, it goes continuously to 0, and when R is beyond R2, it's back to 0. That's the cutoff function. And then we have our repulsive term, quite straightforward, and our attractive term, also quite straightforward. But all the physics is encapsulated in this bond order term, B. So this is related to this function. And what this says is you have to sum over all the neighbors of the atoms. So all the neighbors that are close enough to be regarded as bonded. So basically, you've got a central atom I, and it's got a number of neighbors around it. I, J, L, K, maybe more. So you have to sum over all of those with this function. And so the more of the neighbors is, the bigger this is, therefore the smaller the bond order term is. And that effectively reduces this attractive interaction. So the more neighbors you have, and the closer they are, the weaker this attractive term is. And that's how it basically works. But you also notice here we have the cutoff function as before. So that chooses the ones you're summing over, and you have this angle term, which is also very important, because you can imagine in a silicon, you have a minimum angle you want, a tetrahedral angle, and if you deviate from that, it's going to cost you energy. And that's also encapsulated by this G theta term here. So it will give you the highest binding energy when theta is at the optimal value. So even though it looks complicated and there's lots of parameters, you can see that the physics is actually quite well represented by this material. So very successful and very innovative type of potential in its day. It doesn't work for everything. It's not good for changes, hybridization states for carbon. Therefore, it's not really very good as it stands for hydrocarbons. So there have been a number of modifications. One is the famous Benner potential, actually, whereas the Tersov potential actually sums over sites, the Benner potential sums over bonds. So it actually takes account of the hybridization. It takes account of the number of neighbors for each atom per either side of the bond. The Benner potential is one extension. Another one is a Reboot potential, which actually includes van der Waals. So the way the original Tersov potential could never really have modeled graphite because there are no van der Waals interactions. So all the planes would just have fallen apart. It also includes a torsion term. So there are more modifications than this, but those are the main ones that are probably the most famous ones. And again, anybody using these type of potentials would very strongly recommend to read this review to see all the different options that you can choose for these particularly covalently bonded materials. So I just want to show an example of the challenges involved in actually choosing a potential. I'm chosen here silicon. So silicon is clearly a very, well, you all know how important silicon is, a technological material. So there are many, many different parameter sets that have been used over the years, continuously developed, and some better for other things than others. So this is I'm not going to go through the table. I think it was just illustration to show that actually for diamond structured carbon, all of these many potentials, even the older Stillinger-Webb potential, the original Tersov, and everything since will actually give you the cohesive energy and the lattice parameter very accurately. So this present work was actually a modified Tersov, and it was published in 2007. I'm sure there are many more, but I quite like this one because it did lots of calculations for lots of different types of potentials and compared the results. The point is that the equilibrium structures actually are represented very well by all these potentials, simple ones are not. But once you deviate from this standard equilibrium structure and model structures that actually you would never find naturally, but can be made obviously with density functional theory, and compare how the potentials do, you get a much wider variation. So this type of comparison will actually show you how well your silicon structure will do when you deviate from if you put defects in, if you make parts of it amorphous, you'll see how the energies will do if you deviate from the ideal structure. So they're quite important comparisons. And the same paper actually compared lots of other energies too, the defects, energy, surface structures, all the high temperature, and the liquid silicon. And that's important because you have to choose your potential depending on what your application is. If you're really interested in low temperature properties, such as defects, surface structures, then you're not really particularly interested in what happens in the amorphous state or your liquid state or what your volume change melting is. But if you're actually looking for high temperature properties or even amorphous silicon, then you'd be worried more about your amorphous coordination and how well these strange structures actually do. This is just a pointer to say that depending on what you want to do, you'll have different types of potential. So that's basically the last part of these mini and multi-body potentials. And just to summarize, they're used for materials where the cohesive energy can't be expressed as a sum over the interaction energy between pairs, namely covalently bonded materials, large biomolecules, and metals. So the last part is basically the most complicated, perhaps, and perhaps most ambitious of all the force fields I'm going to talk about so far. So the ambition is that the developers of these types of force fields wanted to model reactive events, such as chemical reactions, and basically bonds breaking and forming. They're interested in combustion and catalysis, and how these could be modeled using classical interatomic potentials. So it's quite an ambitious aim, and they want to be able to model it for all types of materials, not just covalent materials, but covalent anionic materials. So the original motivation was to derive potential forms that could be used to model chemical interactions for applications such as combustion and catalysis. So I wanted the potentials to actually be transferable across all chemistries. So that means if we had an oxygen atom, be able to use the same potential, whether it was an oxygen gas and water and different oxides. So we only have one potential and it should be used everywhere and in different phases. So whether it's in liquid water or gaseous water. And we want to use the same functional form for all types of materials. That means you want to be able to use the same functional form for covalent materials and for ionic crystals and anything in between. I think we're all aware that when we talk about covalent materials and ionic materials, actually most of them are somewhere in between. There's a certain amount of covalency and a certain amount of ionicity. So these potentials are claim or would like to be able to capture this. So this is the general form of the energy of these types of materials, the access potentials. So some of these are actually quite familiar. In fact, most of them are, as you've seen before. We've got the bond energy, the angle energy, the torsion energy, van der Waals energy, and the Coulomb energy. So basically just the same as our multi-body potential. And we've added here over, which I'll explain in a minute, and specific. Specific is something, this means that these don't work for everything, so you have to add something else. And it's not always included, it's just for particular types of materials. The important thing is that there's some very significant differences between this and our multi-body potentials that we had before. And that basically means that our bond angle and torsion angles are all modified by a bond order term. Just as we talked about for our covalently bonded materials, we have a bond order term that we calculate for all, and they modify all of the bond angle and torsion terms of this. And the other important difference is that the bonds are not defined a priori. You just put all the atoms in and somehow the computer works out what's bonded and what's not bonded. So there's no switching function. Everything just depends on distance. The E over is an energy penalty because the bond order term doesn't do everything, and it can actually deviate from the ideal coordination. It doesn't prevent you having 12 atoms around a carbon. So in order to get this over coordination, it will actually help you get to the ideal coordination. So that's what the over coordination is. But apart from the specific, all the other things are familiar, but you have to just remember that they're modified by a bond order term, which needs to be included. In order for the charges, they're actually calculated during the simulation and by using electronegativity equalization. So basically that actually works out what your charge distribution would be in order to the electric negativity in all the atoms the same. This is actually quite expensive computationally. because after every movement, then we have to recalculate what the charges are. So it's one of the significant costs of this type of simulation. As I say, each specific captures properties such as lone pairs that are actually specific to some systems, but it isn't usually needed. And because of the way this are defined, basically, there's no reason why it can't do ionic interactions and covalent interactions using the same functional forms. So that's basically the ambition. So most of my knowledge about these potentials have come from this particular review paper, Computational Materials, which is maybe now a little out of date, but very comprehensive. And these pictures that I'm showing have all come from that review paper. So you start with atomic positions. From that, you can determine the charges using electronegativity equalization, and then we can calculate the Coulomb interactions. We can also calculate straight away the van der Waals interaction because they're just standard. And then we need to work out the bond orders, just because we do that from the positions, and then correct all the bond energies and angle energies and torsion energy from these bond orders and any other terms we need. And then we've got the total energy of the system for that configuration. Then we move them and then do it all again. So as of 2016, there were reaccess parameter sets for all these atoms. So the majority of the ones that anybody interested in modeling should be able to find a parameter set for. This has probably been updated. I haven't looked to see whether there's more added. But the point is that, you know, whatever you want to do, is highly likely to reaccess a parameter set for it. And that's a good thing, because although you wouldn't want to have to derive them. So the original ambition of these original authors was that actually you can use the same parameter set for all types of simulations. This turned out really not to be possible. And the biggest stumbling block was really the difference between the gaseous phase of oxygen and water and the aqueous phase of water. So it started off with the initial ones, the combustion branch, which all work together. So anything in this, any of the parameter sets in this branch all work together. So you can choose the hydrogen atom and you can move it off all these different materials and everything will be fine for all these particular processes. Similarly with the aqueous branch, where they realized that they needed that this combustion branch wasn't compatible with liquid water. It was modified and it came a different branch, and actually all these types of simulations can be transferable. So the oxygen atom can be used in all these different materials without having to change the potentials. And then there's a few ones come straight there and they're a bit different and fall out there. And again, this is taken from the review article and it could have moved on, but I think there are still just the 3 branches. So a summary, it was first developed in 2001. The functional form really stabilized in 2005 and hasn't really changed since then. It's suitable for both ionic and covalently bonded materials, and it includes bonded and non-bonded interactions. The bond order dependence, it makes it successful for covalent interactions, and then this equalization of electronegativity means it's good for ionic interactions, and the charges in the atoms change continuously throughout the simulation, which is a very important point, because if you can imagine for chemical reactions, obviously your charge in your atom or your molecule is going to change as the chemical reaction proceeds. So that's actually a very important part you need to capture, especially for chemical interactions. So it can actually accurately predict transition barriers, and it does long-range covalent interactions, also very important for chemical interactions. And it claims it can model reactive chemistry with accuracy comparable to quantum mechanics. And there's, again, the review paper. It's worth a read. Very good, very clear. So what things can we do? Well, any nanoscale phenomena or complex systems you can tackle with this thing. Basically, catalysis, one of the original aims of the potential set. things like atomic layer deposition and reduce graphene oxide, resistive switching, protein diffusion, nanoindentation. These are some of the things I picked up from the literature that have used these reacts SF potentials. So basically, things that actually need bond breaking and forming, these are the best potentials for. And I've just picked out one of these from literature from Chemistry of Materials in 2020, and that's basically the growth of graphene from silicon carbide. They've taken two processes by which you can actually grow sheets of graphene from silicon carbide and model them with these potentials. One is thermal decomposition. So if you start with a silicon carbide surface and you heat it up, you remove the silicon, you're left with carbon. And that means that these carbon can actually, if you remove it from the top layer, they can rearrange themselves into graphene. So that's one way. There's a technological way of producing graphene sheets. And the other process I've looked at is a reduction of ethene. Basically, you put ethene onto the surface and it takes away the hydrogen, dissolves, and you're left with the carbon, and the carbon rearranges itself and makes graphene sheets. So these are the two types of growth that they modeled using these reacts SF potentials. And they've studied how the structures evolved with time. So the main point about graphene is that you want 6-membered rings. You don't want lots of defects, 5, 7, or 8-membered rings. So in terms of this thermal desorption, one of the important properties would be the substrate temperature. So did these simulations where they gradually remove silicon atoms, and there you can see bottom, as they remove silicon atoms, the graphene structure formed. So the higher the green, the better the structure is. So they found here that the temperature of 2800 Kelvin gives the better structures. So less defects, actually. And so that's their summary of some of the results for the thermal desorption. And in terms of the ethene reduction, yeah, that's basically the same sort of thing. The number of times that the molecule was added to the surface, you can plot the number of 6, 7, 5, 7, 8-membered rings. So you can see that what they actually want is this number to be big and these numbers to be small. And they get nice pictures. You could see all the stones, wheels, defects, and these material and all other sorts of grain boundaries and defects. And they can modify their conditions, rate of deposition, temperature, and see how they can actually optimize the surface conditions. So the reacts SF codes are in lamps, so it's a very common electrodynamics code. The other one, the open source one, is this pure MD code, pure MD code. And these ones, I guess, are not open source, but it means that you can actually use open source codes relatively straightforward in order to use the reacts SF codes. So it's worth investigating for some types of system. So I mentioned this actually earlier when I was talking about silicon. So if you want to choose a potential, what do? Well, first of all, you clearly need to do a very comprehensive literature research to see what potentials are available in the literature. You probably want to try and avoid refitting a potential, whether you may want to be able to do some tweaking of the potential, pre-existing potential, in order to fit more what you're trying to do. So which properties do you want to model, and which are different potentials been fit to? So you have to be aware that they've been fit to some potentials and they may not be, as I said in the beginning, they may not be appropriate for potentials too far away from this. So which properties are most important to you? Are they thermal properties, or the mechanical properties, or defect properties? And then which codes would you like to use? Which codes do you have expertise in? Which codes do your groups have expertise in? That can save you a lot of time from starting from scratch And some of these are easier to use with different types of potentials than others. Okay. We also like to point you to this OpenKim website. So this is an interatomic potential repository. So it's trying to get together all potentials of people that develop potentials, put them or use potentials, can put them in this repository. It's a very easy place to see what's been done. So if you have a particular material you want to model, if you go to the website and just click on the element, you'll find what interatomic potentials are available. So it's a good place to start looking what's available. It also has a support, so you can actually test potentials using these three well-established, very common molecular dynamics programs. So that's basically the end of this lecture. So where are interatomic potentials going next? So what I like about interatomic potentials is the physics base. So the functional forms that have been developed so far relate to the physics or the quantum mechanics of the bonding. And I think that's quite nice because it makes you understand what all the different parameters, you could see quite easily from the two-body potentials, where the parameter, what the physical properties the parameters related to. Maybe a bit harder for the more complicated ones. So these are being continuously, people are continuously developing more and more potentials for all different types of systems. I think it's a continuous development. But in terms of machine learning, is becoming more and more popular and becoming more and more powerful. So I think it's going to be more, but you'll learn more about that. I think it's next week. You'll learn more about machine learning, certainly worth following. And it seems to be very successful so far. It does require a very large number of very high level, highly accurate electronic structure calculations, because if you try to fit these things to dicey calculus, like all these things, if you try to use not so accurate calculations, then you're probably not going to get good potentials. But I think it's definitely the way things are moving towards, maybe not for all materials, but for some. And I will finish there and see if anybody would like to ask any questions. Nope.
No.
No questions?
No.
Okay. Well, in which case I'll let you get on with your day and wish you all the best for your rest of your time at the TYC.
Okay, thank you.
Okay, bye.
Bye.
Thank you.
Thank you.
Bye.